All right, problem number 7 through 10, Algebra 2, homework 4.1. Let's start with 7, 8, and 9. Again, this is Algebra 2, HW 4.1, and MTS. Okay, so to define whether this is growth or decay, is this less than 1? So it's 1/3, right? So that's less than 1. So therefore this is decay. Okay. Now this is less than 1, but it doesn't matter. The only thing we care about is this piece right here. Because that is greater than 1, right? 1.3. Then this is an exponent. This is what we call growth, exponential growth. Okay. And then here with number 9, 10 doesn't matter, but the 2.7 does. And isn't this to the x? Sorry about that. So 2.7 is bigger than 1, so it is growth. And so now let's look at the story problem, which is number 10. And if you're at home, you want to probably push pause and read the story problem. So the amount of the freight transported by the rail in the United States was about 580 billion ton miles in 1960. And has increased at a rate of 2.32 a year since then. Write a function representing the amount. Now the function, since it's growth, right? It's increasing. So that's something we want to make sure. Okay, so we know it's increasing. So if it's increasing, we're talking about growth. So when we're talking about growth, we are talking about f of t, or actually a of t is equal to a times r plus 1 to the t. Okay, and we're using the growth model. So the growth model is going to, we need to plug in the stuff that are constants. T is our variable, but our constant is going to be the rate and the amount we started with. The amount we started with was 580 billion, right? Ton miles. That's the A. Okay? Okay? So R, the rate is going to be the rate of 2.32 a year. So 3.32%. Now remember, that's in percent. To change percent to decimal, if it's at 3.32%, to change it to decimal, we're going to move it over 2 places, because basically you're dividing it by 100, right? We're going to put the decimal here and fill in the cup. So the rate is going to be 0.0332. Okay? So the function is going to look like this. A of t is equal to 580 in billions, right? So this is going to be in billions, right? Times 0.0332 plus 1 to the t. And this is part A. Part A says write a function representing the freight per tons in billions. And then they said for, and that's year 0. Okay? Now they want you to graph the function. Okay? So if we were to graph this, I can actually show you. It would be similar to this. I'm going to take this off. Put this down. Bring this up.
3290 or dot?
Which one?
The 3.329.
No. 3.329. Where?
The purple.
3.32. Oh, that's the percent.
Okay.
So 3.32%. Come on, there's my graph. Alright, so here's my graph. And if I wanted to plug it in, then it would be y equals. So it would be y equals sorry. I gotta use their y. Y equals, and then I'd be 580, right? And I could put billion. I mean, I don't think it matters. I mean, I guess like if I put in billion, then it'd be like 1, 2, 3, 1, 2, 3, right? So that would be yeah, no, that would be million, right? 3 would be thousands. 3 more would be millions. 3 more would be billions. And then parentheses. 1.0332, and then in the parentheses, and then raised to the power of t, or x. So where's my caret? A to the b to the power of x. Alright. And then that would graph, but see the graph, I have to zoom way out, right? There it goes. So there would be my graph. Okay? Now watch this. See how much this graph changes if I change this from billion scales? See what happens to it? If I just said 580. All I'm doing is, the graph is the same, but where it crosses on the y-axis, this would still be the same spot, right, at 580, but that would be at 580 billion. So in other words, what we're doing is, we're just saying that the scale is in billions. Does that make sense? Nothing really changed, except for the fact that now I took this and took it out of billions. Now I could put it in billions, it just makes your scale get really big. Okay? Oh, I guess you guys can't see that. So let's show you guys what I'm talking about. So that's in 500, and then as we talk about billions, we go 1, 2, 3, 1, 2, 3, 1, 2, 3, right? And then if you look, we go out farther. We go out farther. We would get out to billions, and it wouldn't hit this. And it's hard to see, but it wouldn't hit until it hits at billions, and that's at 580 billion, right? So it's really hard to see on that kind of scale, and that's why I say, okay, just change your scale by telling yourself that this is in billions at 580 billion, and now we can zoom in, and it'll be a lot easier to tell where it's crossing at 580 And then you can go up here and put this right here. It goes 0, 580. Okay? Alright, so that's what your graph would look like. That's part B. And then part C was how long does it take for the half dose to remain? For half of the dose to remain. Oh wait, that's the medicine one. Sorry. In what year would you predict the number of ton millions would have exceeded or would exceed 1 trillion? So at 1 trillion, what is that? That would be at 1,000, right? So we're going to look for 1,000 on here. Like, where is the output at 1,000? So we got to kind of look, the other direction. And there it is at 1,000 right here. And at 1,000, you're looking at about 17, right? Instead of 0. So it's 17 years later at 1,000. So what's 17 after, what was this based on? 18 or 19? 1960. If this was in 1960 and 17 years later you would be at 1 trillion, what year would that be?
This one said 19.
Did it? No, number 10 says 1960. Yeah. What? Oh, it says 24 years. At 1 trillion? Huh. So let's do the math. The way we would figure that out is this would have to be 1,000, right? Or 1 trillion. So 1 trillion would be 1,000. So 1,000 is equal to 580 times this. We want to know what t is. Oh, but we'd have to know logarithms to do that. Plus 1. So I guess if we're looking at for some reason our scale is showing that it would happen at 17, because 17 would give us 1,000. Did it say 1 trillion? Right? And this is 580 billion. Right? And 1 trillion would be 1,000. So at what point, so if we plugged in 17 on that on our calculators, what would we get? Let's try it. So that's kind of what we're doing in this class right now. We're just plugging and chugging. So we're saying, okay, 1.0332 raised to the power of 17 is equal to a number. We multiply that by 580. Yeah, 1,010, just like our graph says. So it should be in 17 years. I agree with the graph. I don't agree with the book. I think the graph is pretty accurate, and since I came up with 17, I tried it, and it works. I think it would be right. Now, let's see, maybe the math is different when we do billion, right? So I don't think so. We'll try it. So we'll go 1.0332 raised to the power of 17 equals, and then I'm going to multiply that by times 580. Oops. 580, and then 1, 2, 3, 1, 2, 3, 1, 2, 3, and then equals, 1 trillion. So I think we're good, right? So So 17 years, or in other words, I would say 1977.